The program ROM for Super Mario Bros. Contains 32,768 bytes. 22,790 of these bytes are for CPU instructions, while the remaining bytes are raw data such as the levels, music, or animations. We could dilly-dally and put more statistics on screen, but we've got more important business to attend to. Keep in mind, in a typical 100% completion of a video game, using Super Mario Bros. 3 as an example here, you have an arbitrary checklist of things to do. Whether you are playing levels that could otherwise be skipped, fighting bosses that could otherwise be skipped, or collecting items that you wouldn't even need in a casual playthrough, the idea is to do it all. But if you think about it, if you never saw the words game over, did you really do it all? In this run of Super Mario Bros., I've got a checklist of 32,768 bytes that I want the CPU to read. I want to run every line of code and read every byte from every table. Welcome to ROM maxing. Let's power on the console, and for now I'll highlight the lines of code that run and the bytes that are read each frame. By today's standards, 32 kilobytes is not a lot, but even at this scale the code is entirely unreadable, so I'll be zooming in when needed. All you need to know is that the code has branching paths that are taken depending on what's happening in the game. Is a Goomba on screen? Run the movement and collision subroutines for the Goomba. And likewise, the game would never run the code for, say, Mario's swimming movement if you never entered a water level. Let's begin. I'll highlight every line of code that we haven't ran yet, so once we're nearing the end of this run, we can easily see what we missed. By powering on the console, we can see just how much code goes into loading the title screen. Once Mario's on screen, we're also running all of his movement and collision routines. All we have done so far is push the power button, and we have already seen 16% of the ROM. If you let the title screen demo play out, you get scrolling the screen, loading new tiles, loading enemies, the Goomba routines, bumping a block, collecting a coin, moving a mushroom, collecting a mushroom, taking damage, and dying. We're looking at 31.9% of the ROM, and we have provided 0 controller inputs so far. With minimal planning, let's just try and do everything. I'll start by selecting 2-player mode. Touch the left edge of the screen, bump a brick, crouch, collect a 1-up, transform this Goomba into a Koopa. You know, normal gameplay things. The issue with a run where you have to do everything is that it's not always immediately obvious what everything entails. I basically started this run by trying to do a bunch of glitches that I would probably have forgotten to do later, like the graphics buffer overflow. My main goal at this stage was to at least run through every room in the game, and then I'll go back and see what code I missed. Pop quiz, hotshot, what level is this? And about an hour later, I saved the princess as Luigi, got a game over as Mario, and began the second quest run. Goombas are now replaced with Buzzy Beetles, so that's some new code, and so on and so forth. Cool run, Mario, but it looks like you missed 459 bytes. There was a lot of pretty easy stuff I missed in this initial run. Don't worry, I did take care of all of these, but I want to focus on the more amusing stuff. Now here is where this run gets interesting. If you're just sprinting through the game as fast as possible like I was, then you never let these oscillating platforms or red paratroopers complete one cycle of their oscillation. Likewise, if you're always moving as fast as possible, then Flying Cheep Cheeps and Lakitu won't be able to run some of their code. Amusingly, if your horizontal speed is 0, they behave differently. Speaking of Flying Cheep Cheeps, they have 16 random positions they can choose to appear in, and 12 random speeds they could enter with. It took pretty much the entire level's timer before I actually got all of these. Can you imagine the world's worst speedrun category, where it's like, oh, you never collided with the side of a spring? That was a requirement. Shifting the focus back to Lakitu, there's an interesting situation surrounding what happens when he respawns. The game has 6 sprite slots, which are basically just a series of bytes reserved for enemy data and a handful of arrays, and each slot is processed starting at slot 0 and working up to slot 5. If a slot is occupied, run the routine for the sprite loaded there. Otherwise, run some code that checks to see if a new enemy should be spawning in. This means that empty sprite slots run the code for checking if something spawns in as the screen scrolls, or handling the stages with infinitely spawning enemies. The Lakitu falls under that latter category, which means if there are any empty sprite slots, Lakitu can run code for respawning. Otherwise, this code doesn't run. This code for respawning Lakitu checks each sprite slot for availability, and it puts Lakitu in the first empty slot it can find. However, what's logically impossible to occur is if all of the sprite slots are full, in which case there's a failsafe to abort. This is an example of unreachable code. In order to run this BMI instruction, we would need to simultaneously leave one of these slots empty and have all of them occupied. You can see the issue. It would seem like the only possible way to run this line of code would be through major exploits, such as arbitrary code execution. Now is a good time to mention that one of my arbitrary rules that I have imposed on this run is no shenanigans with the cartridge port. Super Mario Bros. Must remain correctly inserted at all times. This restriction alone prevents the only known method of running arbitrary code in the cartridge release of Super Mario Bros., and by preventing the only known method of running arbitrary code, we've also prevented any possibility of running this, as far as I can tell. But sometimes it's not immediately obvious if the code is unreachable or not. For instance, when you complete a level, Mario lowers the flag on the flagpole, but there's a failsafe in case the flag is missing. Mario would just hop off the flagpole. I've seen this used in speedruns of Super Mario Bros. 2 for the Famicom Disk System, and I wonder if we can make it happen here. But how do you despawn the flag? Well, let's ask the expert, former Warpless World Record holder GT Ace. Do you want to tell us how this works?
No.
If he would have cooperated, you would have learned that the flagpole flag always occupies the final sprite slot, but the tiny star flag that you see after beating a level can actually overwrite this sprite slot if no empty slot is found. If you were to make it to the end of a level with 5 enemies on screen, the star flag will take priority over the flagpole flag, despawning it. The key issue here is that the staircase makes it pretty much impossible to bring enemies to the flagpole. In order to pull this off, we're going to need to send these Koopas on a magical adventure. When an enemy is below ground level, they stop detecting walls. And while in this state, if you stop them, they act as though they are on a floor even when they absolutely are not. And Koopa's magical adventure might just be the trick we need to despawn the flag. I chose to do this in World 8-2 since there's a lot of Koopas and a lot of pits. It took a while to task this, but once I had all 5 sprite slots in their magical adventure mode, I could walk through the rest of the level without seeing a single other enemy. Just like that, we despawn the flag and get to run 3 new bytes. Yeah. Let's talk about these balance platforms. If you stand on one, they gain momentum and draw tiles on the background to give the illusion of rope sliding around. Keep in mind, they only draw these tiles while attached to the pulley. Once broken, they stop drawing. If you were to somehow move one of these off screen while still attached to the pulley, there's code to prevent the tile from being drawn. You know, off screen. There are bugs you can exploit to extend the length of the rope, but once it's low enough on screen, Mario stops colliding with it. So this code appears to be unreachable. Let's circle back to that one. Did you know that these platforms have a speed limit? Probably not, because it's 3.5 pixels per frame, which is significantly faster than you can accelerate one of these before it reaches the extents of the pulley. Every object that uses gravity uses the same subroutine, but this is the only object that uses the upwards gravity subroutine. The half of the balance platform that Mario isn't on accelerates upwards, and this upwards acceleration subroutine handles speed limits too. Incorrectly. Instead of limiting its speed if it is at the speed limit, it limits its speed if it is greater than the speed limit, so you would need to make this platform reach 4.5 pixels per frame to run this code. But perhaps not all hope is lost, because we have a trick called sprite inheritance. These balance platforms track which sprite slot the paired platform is in. If the paired object unloads, the platform is still linked to it, and if anything new loads in that slot, it gets treated as the other half of the balance platform, even if it's not a platform at all. These levels were carefully designed to occupy all the sprite slots with these platforms, unloading old ones just in time to load new ones in, but we can easily break this by utilizing Koopa's magical adventure. This can be used to make this oscillating platform act like a balance platform. You can see how it draws tiles while moving downwards and erases tiles while moving upwards. But more importantly, we can take it off screen. That takes care of one of these two labels, but what to do about the speed limit problem? Well, to make a long story short, even using sprite inheritance to inherit the platform's momentum doesn't work. Or at least, I couldn't make it work. I think this upwards gravity speed limit code is unreachable, but feel free to task this and prove me wrong. Alright, what have we not investigated yet? The tables for every level's sprite information ends with a terminator byte, telling the game to stop spawning in enemies after this point. But sprite loading behaves differently after Mario touches the axe. As mentioned earlier, sprite loading only runs if there's an empty sprite slot, but in the post-axe touching mode, there's only a single sprite slot which gets filled in by Toad. With Toad occupying the singular sprite slot, the game never attempts to read more object data, so the terminator byte is never read. And since there are 6 unique castle stages, that creates 6 unused terminator bytes. To my knowledge, it isn't possible to read these, so they're left unread. The tile data for the background bushes and clouds actually have unused data. These zeros never get read while drawing the background, but that's not going to stop me from trying. The background actually repeats every 3 screens, but if you were to somehow run over 131 screens to the right, the routine that draws these backgrounds will begin to malfunction. But why? Let's see how the game determines which background to draw. To make a long story short, we compare what screen we're drawing with the number 3. If the screen number is less than 3, draw that screen. Otherwise, subtract 3 from this number and keep doing this until this number is less than 3. Unfortunately, they decided to use a BMI instruction here instead of a BCC instruction. And the reason I'm saying this is unfortunate all has to do with exactly how the CMP instruction sets the processor flags. Essentially, this instruction subtracts the operand from the A register, and if that signed value is negative, then set the negative flag. Also, if the A register is greater than or equal to the operand as an unsigned value, set the carry flag. And also the 0 flag if the numbers are the same. Branch on minus would be perfectly sensible if you are using a signed value, where negative numbers are taken into consideration, but this function is hoping to only move forward with the values 0, 1, or 2. Branch on carry clear would only be taken with the positive numbers that are less than 3, which would have prevented this bug. Anyway, since this bug exists, we can draw screen negative 125 through positive 2, and some of these negative screens read from the unused background tiles. Wait, hold on, how do you even run 100 screens to the right? First of all, the flagpole is in the way, and second, wouldn't the timer run out long before then? Ah, well you see, you can clip into this floor, break some bricks, and then touch the flagpole. Mario will keep running until he collides with something, which will never occur. We will eventually need to hit the console's reset button, but we'll read these bytes first. This table here, a jump table for sprite initialization routines, has a shocking amount of unread bytes. When a new enemy spawns in due to the screen scrolling, this table determines what initialization code to run. Notably, piranha plants haven't been initialized this way. In any level beyond 1-1, it's the pipe tile generation routine that places the plant, rather than the empty sprite slot checking for the screen scrolling. But also, just look at how many other bytes we're missing here. Most of these would jump to this label here, no initialization code, but we're also missing a type of short firebar. This short firebar taunts us with a few more bytes, giving it a unique combination of slow movement while going counterclockwise. But just like the unused bytes in the background decorations, I have an idea. There's a method of corrupting the enemy data of water levels. Specifically, it only works for World 2-2, 7-2, and 36-1. In 2-player mode, if one player dies on a water level and then the other player dies while climbing a vine, the enemy data inside the water level becomes corrupt. But why? Once you reach a specific point while climbing a vine, a flag is set that will spawn a vine in the next loaded room. When you enter a room that needs to spawn the vine will appear occupying sprite slot 5. And the code that runs immediately after this initializes the bubbles for water levels, under the assumption that the X register will be 0. However, since X is now 5 due to the vine, the game will attempt to initialize index 5 of the bubble positions. But there are only up to 3 bubbles at a time, so we're writing beyond the intended bounds of the array. The Y position, written to address hex E9, overwrites the low byte of the pointer used to load enemy data for a stage. So instead of reading from this table of enemy data, as intended, we read from this table of tile data from World 1-4. Treating tile data as enemy data gets a lot of garbage that takes care of a handful of otherwise unused enemy initialization routines. And check this out, we got both a piranha plant and that otherwise unused firebar on the same tile. Repeating this from every checkpoint in every water level takes care of an already stomped red paratroopa, already stomped green paratroopa, piranha plant, the unused firebar, and a mushroom. And yes, these stomped paratroopas are technically different than the regular Koopas. And at this point, I think that's as much as I can do. Here's what's left. Unused, unused, impossible, unused, 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 impossible, 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 unused, impossible, unused, impossible, unused, 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 impossible, unused, 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 impossible, unused, 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 impossible, 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 unused, unused, unreferenced, 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 and unused. You can read my footnotes for all of those to see how I came to those conclusions. By the way, I'd like to mention that so far, all of this has been for the program ROM of Super Mario Bros. We haven't even taken a look at the character ROM. Are there any graphical characters we haven't seen? Well, let's find out. Here's the character ROM of Super Mario Bros. You probably already noticed these garbage-looking tiles on the bottom row. Well, we certainly haven't seen these anywhere in-game, right? What's going on? The picture processing unit has in fact read these characters, and it happens very briefly after powering on the console. Also, as a brief tangent, when the picture processing unit reads from this stuff, what does that even mean? These are still bytes, right? What byte values would you read if you wanted to read from a specific character? Every pixel of these characters is a 2-bit color. Let's separate the high and low bits into their respective bit planes. Since each of these characters are 8 pixels wide, we have ourselves 8 bits per row, which gives us a total of 16 bytes per character. Back to these garbage-looking tiles. The game reads all this and stores it in RAM, but what is all this stuff? Well, these bytes are in the format that Super Mario Bros. Uses for its graphics buffer. The first 2 bytes form an address pointing to a location on the background's name table. The following bytes get a bit more complicated, but to make a long story short, this data is used to draw the title screen. Pretty cool, huh? I guess they ran out of space in the program ROM and had to put all this data in the character ROM. And with that mystery taken care of, let's run the exact same inputs I made earlier, this time taking a look at the character ROM. Just like before, I'll show the full table now, but darken the character if the picture processing unit ever reads from that address. As it turns out, we missed 2 characters, J and X, and about half of this character. These 2 are actually pretty easy to draw. Once you go above 10 lives, you get this little crown on the screen transitions. But if you keep going, the lives counter only shows a single digit. Going above 10 more lives will start drawing further characters from the ROM. We just need to get the right amount of lives, and we can see any character we want. At least, any character up until this one here. Going beyond 255 lives will loop back around to 0, so we lose the crown and simply have 0 lives. That means we're still missing these 5 bytes. And that's as far as I was able to push Super Mario Bros. With the research I was able to do on the cartridge release of the game, there are 206 bytes remaining in the program ROM and 5 bytes remaining in the character ROM. But this probably isn't the limit. I bet you can use the graphics buffer overflow to draw that character I missed, though I'm not super familiar with how to manipulate it. I didn't optimize this at all, by the way. The entire run is 2 hours, 5 minutes, and 54 seconds. But you might be wondering about the Famicom Disk System release of the game. You know, real quick, let me add FDS support to my emulator. Well, I am a husk of the person I was 2 months ago, but it runs. Anyway, I was going to talk more about the Ace exploit in this version of the game, but I'm just gonna save that for its own video. I'd like to take the time to thank you for watching, and an extra special thanks to everybody who supports me on Patreon. These videos are brought to you by viewers like you, so seriously, thank you. I'm planning on making a post on my Patreon going into the behind the scenes of this video, if that's something you're interested in. And if you're looking for even more ways to support me, and also get a playable video game out of it, ho-ho! I've got a keyboard and mouse platforming game called Fantastic Fist that's currently 80% off. Anyway, I'm gonna make a video that requires less intimidating research so it doesn't take 7 months this time. Sorry about that.